Imagine a pendulum of two balls, one that is at rest, perfectly perpendicular with ground, while the other is suspended 45 degrees in the air, but is then released, hitting the other ball at rest. They both have the same length of string, but different mass. What is the maximal height that each ball reaches after the collision occurs? In this situation, we will use a system of the two balls and the earth, implementing the laws of conservation of energy and work energy theorem. We will use an ideal pendulum with massless strings, ignoring air resistance. We will also assume no energy is lost into heat or sound upon collision, and that the balls only move in two-dimensional space. We will also ignore any other possible forces of gravity.
Alright, so we're going to start by defining our system over here. We can call this 0, which means that this distance would be h0 from what we have defined as 0 all the way up into the first ball's initial height. Therefore, this dotted line distance right here is equal to L minus h0. And through some simple trig, we're able to calculate h0 equaling L minus L cosine theta. We can also set these two angles equal to each other, and we know that these two strings are equal to each other. So this is how we find h0. We're now going to move on to defining timelines or instances. So instance A is going to be from this very starting point all the way up until the ball is right about to hit ball number 2. So right before ball number 1 hits ball number 2 from the start, that is this instance in time right here. So we have identified the energies of the balls during this position. So the initial energy of ball 1 is all potential because it's hanging from the string. And right before it hits the ball, it's all been converted to kinetic energy. The energy of ball 2 is just 0 the whole time because its net force is 0. So therefore, its energy is 0. Instance B is going to be the instant right after the two balls collide. So in this instance, the initial energy of the first ball, which is really just this, is still kinetic, and the final energy of the first ball is kinetic right after the two balls collide. It's not going to stop right after hitting the first ball. It could, but we're going to assume that's not going to happen. And for ball 2, it started off with 0 energy, but now it has some kinetic energy from the first ball colliding into it. So we're going to be referencing these instances throughout. So first, let's look at mass 1 timeline. So this is going to be instance A. We know that its initial and final energies are potential and kinetic, so we can set mass of 1 g h naught is equal to 1/2 mv squared. This is the gravitational potential energy equation, kinetic energy equation, and substituting in h naught, we can get that the velocity is equal to this right here. Notice the masses cancel. Now, the momentum from when ball number 1 hits ball number 2, right before it happens, or when it is happening, it's equal to m1 v1, which, doing some simplifications, we can say that the momentum when ball number 1 hits ball number 2 is equal to the mass times the velocity that we just calculated. It's a pretty simple calculation. Now, if we move on to instant B, and we assume that horizontal momentum is conserved at the instant right before the balls collide, then we can say that the final momentum is equal to the initial momentum at different instances that we have described. So we can say the final momentums of ball number 1 and ball number 2 is equal to the initial momentum, which is also this right here. This is the initial momentum going from instance A to instance B. That is why we are able to make the distinction that this is equal to this. Now, we have this thing flying around here, and in order to make the calculations easier, we're just going to set it equal to u, and we're going to be using u a lot here. So plugging in this, setting it equal to these two, we can say that potential energy at instance B of ball 1 plus potential energy at instant B of ball 2 is equal to the mass of ball 1 times u. So that's kind of our first equation that we're going to get here. Our second equation due to the assumptions we've made, we can assume that energy is conserved during instant B, which is an elastic collision. So there is no energy lost in the system. Therefore, the initial kinetic energy is equal to the final kinetic energy. The reason these are kinetic energies is because of this right here, which we have already established. So we can say that 1/2 mv squared, which we really set as u, plus 0, because the initial energy of ball 1 in instant B, or the initial energy of ball 2 in instant B is 0, is equal to both kinetic energies after, because after both balls collide, they each have some kinetic energy. So doing some simplifications here, we can cancel out a 1/2, and we have this equation right here. Okay, sorry, quick thing. That should not be there. So now we have our relevant quantities identified here with the momentum equation, the energy equation. We can solve for V1 using this equation. We get this. We can plug it into the energy equation, and through a lot of algebra, you can pause if you want to solve it. We put some tips here of what we kind of did, but essentially through a slow arithmetic process, you're going to get V2 is equal to 2 times the mass of ball 1 times U divided by the sum of the masses. Okay, so now we can add a little definition here, the velocity of ball 2 after it's been hit, and we're going to introduce a new instance. This is instance C, when both balls the collision's already happened and they're both moving up to their final position. Both balls will start with kinetic energy and they will both finish with potential energy. So if we take this equation right here, knowing that energy is conserved from previous explanations, we can say that the initial energy is equal to the final energy, which means that the kinetic energy is equal to the gravitational potential energy right here. We can substitute in the equations and get a symbolic answer for what the height of ball 2 will look like. Now, if we plug in this velocity, which we previously calculated, then we get this equation right here. It's this divided by 2g, and through some more algebra, we can do this and do this. You can again pause it to see if it makes sense, but we get some simplification, something canceling out, and we get this answer right here, which we're going to review in a second. Okay, so we've been paying a lot of attention to instances. Let's kind of pay attention to the whole thing as one, from the start of the movement all the way to the end of the movement. Once again, we know that energy is going to be conserved, so we can say that the initial energy is equal to the final energy. Taking the initial energies from instance A, the start, the most beginning part we can do, and the final energies from instance C, the most final energies we can do, we can set the equations here equal each other with substitution. So we have u grav 1 plus 0 equals u grav 1 plus u grav 2. But keep in mind that u grav 1 and u grav 1, these are not the same, these are different because the height of ball 1 is different at both times, which you'll see when we actually start plugging in variables. You're going to see a different height right here. So these two are not the same thing. We can cancel out a g. We can make some simplifications and get a symbolic answer for height 1. And we just found the second height, so it's going to be a little bit nasty, but and we can't simplify this anymore. We tried, but this is going to be your equation for height 1, and we're going to do some further analysis on that.
Quick unit check here for heights 1 and heights 2. Here in our equation we have height 1, and through our plugging in height 1 we get height 2 over here. And so when we work out our units here, kilograms times kilograms meters over kilograms. These kilograms cancel and we're left with meters for height 1, and height 2 over here we're left with kilograms times meters over kilograms. That cancels, and for height 2 we get meters.
So we can do some sense making with numbers here. A length, we can pick a pretty reasonable value as 10. Same with theta, it looks like to be at like about 60 degrees or something. But for the masses, we can have mass 1 be 1 kilogram, mass 2 be 100 kilograms. We should expect if our equation for height is true, then when that low mass hits the heavy mass, it's not going to move at all. So if we plug in values into this equation, we find that doing some simple simplifications, you get that the height of ball 2 is this, which is barely nothing. It's a very small value, which proves our theorem correct that when you have a very high mass and a very low mass hitting the high mass, yields a small result, backed up by our equation for height. So this makes sense.
Here we have some more case analysis. A question here, what if ball 1's mass was equal to 0? Well, let's see what it would do to our maximum height here. So in our first equation here, for the height 1, we see that there would be a 0 in the denominator, which means that we would have an infinite height for ball 1. This makes sense. If our ball is massless, it'll hit ball 2, which would be equal to 0 in this next equation, which would be unmoved. And then ball 1, being massless, would hit ball 2 and extend infinitely upward. In reflection to what we've covered and learned in this class, our pendulum problem is similar in that it uses the conservation of momentum and energy, and different in that they're both used in the problem. This is something that we haven't tackled at the same time in a more complex problem. This overall complexity is in putting all the pieces together, which involves a lot of variables and algebra. In reflection to what we've learned and covered in this course, our pendulum problem is similar to energy momentum problems in terms of their setup, diagram, and assumption making. Good examples of this are the ball drop problem in week 10 lecture and the water slide and spring exercises in the week 8 lecture. All of these problems first had to start with defining a system. In doing so, we could then use the conservation of energy to set the kinetic energy of the initial equal to the final. You see, when we have a work net external equal to 0, we can then use the conservation of energy, and in doing so, we can set the kinetic energy of the initial equal to the final. And this is only possible if the work net external is equal to 0, which we can make 0 through the way we define our system. What's interesting and different with our pendulum problem is that we use the conservation of energy as sort of a stepping stone for finding the velocity value of the second ball when we use the conservation of momentum. When we do find the velocity value of the second ball, we then put it back into our conservation of energy equation, and then we're able to solve for the height of the second ball and use that for the max height of the first ball. Despite being more difficult in terms of the algebra involved, the conservation of momentum aspect of our pendulum problem is similar to that of the week 9 homework problem 1 involving the astronaut. We would use our isolated system of objects in our elastic collision to apply the conservation of momentum, which means that the change in momentum is equal to 0, and therefore the initial momentum is equal to the final momentum, which then allows us to more specifically solve for the final velocity in the astronaut problem and for the velocity of the second ball in the pendulum problem. Overall, this pendulum problem that we just covered is very fitting to wrap up the Physics 211 term because it takes a lot of the topics that we've covered and pieces them together. This includes energy, forces, momentum, understanding diagrams, and sense making. Thank you very much for your time, and have a wonderful rest of your day. As we say it back home in Hawaii, aloha!